We continue with the flip-flops. We talked about edge trigger flip-flops, and now let's talk about timing of these edge flip-flops and Verilog description, and also some flip-flop controls. Okay. Let's do a little bit of flip-flop control and do a little bit of Verilog. Okay. Here I'm using falling edge. Let's look at the first one. I guess I already done this. It is always on the neg edge of clock. Q gets D, if this is D. Okay, and this is clock. Let's not worry about Q bar. You can do an assign Q bar. And remember that Q has to be rich. And if I add an asynchronous reset active high, then this becomes always. Okay. Let's do two changes. Make that active high and remove this bubble. So that becomes always on the pause edge of the clock, or when this is clock, this is reset, or when reset becomes 1, that means pause edge of reset, flow begins if reset is 1, or let's say do this 1 tick B1, then Q becomes 1 tick B0, else if reset is not active, Q gets D. Okay. I can add an enable as a control to my flip-flop, meaning that if the enable is active, only then clock is active. A symbol is this. This is an enable. And I call this one enable 2 and put the 2 on the left-hand side of the clock. What it means is that my clock is no good unless enable is 1. Okay, let's write the Verilog description for that. Okay, so let me show the symbol in red to write the Verilog description in red. Okay, it works like this always. Here is neg edge of clock. I'm calling this one CLK. I'm calling this one DIN. I'm calling this one EN or enable. This is positive edge. If enable, then Q gets D in. Otherwise, nothing. Okay? Otherwise, nothing. Nothing means that Q doesn't get D in. What does Q get then? Nothing. That means the value is retained. Therefore, only if enable is 1, D in goes into Q. Otherwise, D in doesn't go into Q. Let me do one more, find some space and do one more. Or no, let's not change the color of this because that becomes a little bit confusing maybe. So let's do this. This is a flip-flop, rising edge flip-flop, C1, Q. This is 1D, and this is 1R. This is my reset input. This is my D in input. This is my clock input. Okay. The difference between this and this second one is that I have a 1 on the left hand side of the R. Remember, I said when you have a 1 on the right hand side, it means it is controlling. If you have a 1 on the left, if you have that same number on the left hand side, that means this is controlled. What I'm showing here is that the reset is not an independent reset. This reset is a reset that is controlled by the clock. So let's describe this in Verilog. Okay, once again, the input output always the same. The output Q has to be reg always. On the, this is pause edge, clock. Okay, all right. Now then put reset in the sensitivity list, because reset cannot by itself come in and do anything. Clock is the one that controls even the reset. And therefore, okay, I come in. If I come in on the clock and I find that reset is active, then Q gets 1 tick B 0. Else, if reset is not active, then reset is allowing Q to get D. Okay. Let's do the implementation of some of what we just saw. See, what I'm assuming here is my internal the internal of my flip-flop has an enable. What if I don't, or what if I don't have an enable and I like to have an enable? That's one question. The other question is the this one on the right hand side. I'm assuming that the internal of my flip-flop has a synchronous reset. This is synchronous reset. Okay, what if it doesn't have? Can I add one to it? So let's do this. Let's say this, the one on the left hand side is a flip-flop, and I like to add an enable to it. I'm not able to touch the flip-flop. I'm not able to go inside the flip-flop. I want to add an enable to it. Okay, one thing you cannot do is you cannot gate the clock. You can never gate the clock. You can never delay the clock. You can never put logic on the clock. You can never get the output of a. You can never put output of a flip-flop into the next clock. You cannot play with the clock. Respect the clock. So if I don't have an enable, I'm not gonna put an AND gate or an OR gate on the clock. That I cannot do. So what can I do? I'm gonna put a multiplexer here. And then I'm going to put my enable input here. If my enable is 0, the output comes back through the multiplexer. If enable is 1, only then the D in goes through. So this is falling edge. The flip-flop with clock enable input. Okay. What if I want to add a reset? And this is the second one, is the flip-flop that I have. Okay, remember here, the red one is let's see, where do I have the reset? No, the this was the reset. That's okay. This is all I have. I cannot go inside that, but I do want to add a reset to it. The only reset I can add to it is a synchronous reset. Okay? I cannot go through this, so I have to go through my D input. This is how it works. Okay? If reset is 0, nothing happens. When reset is 1, then on the falling edge of the clock, D in goes into, on the fall, if reset is 1, you have a 0 here, and therefore a 0 goes into Q. So this behavior is the same as this one here, that the reset is controlled by the clock. And this is exactly how I would write the Verilog description of it. Okay? What if you have a situation that you want to add a preset to it? Okay, I want to add a preset to it, and again, I cannot touch the flip-flop, and therefore what I do is if I want to add a reset, I put an AND with the reset, and if I want to add a preset, I put an OR with preset. Okay, or the set input. Set. And then this is my DN. Okay, let's write the Verilog description. Always on the neg edge of the clock. This is being clock. If I am giving priority to reset. If reset on the clock, Q gets 1 tick B0, else if set on the clock, Q gets 1 tick B1, else only then Q gets DN. Okay? So these are flip-flop controls. If the flip-flop has a set or reset inside it, you can use it and it's asynchronous. If it doesn't have it, you have to have set and reset. The only choice you have is to add external logic to it and do that. If you have a D flip-flop, you decide that this is not good, you want to turn it into a T flip-flop, you can do that. If you have a D flip-flop and you want to turn it into a JK, you can do that here. D flip-flop. You like JK. This is J, this is K. Bring Q into this logic, design this logic, okay, as such. JK, Q, and D, which becomes your Q plus. If J is 1, you want to make sure that this becomes 1. If K is 1, you want to make sure that this is 0. If J and K are I'm sorry. If JK are 0, 0, okay, Q plus remains the same. If JK are 1, 1, Q plus becomes the complement of Q, okay, D, which is the same as Q plus. If JK is 0, 1, you want to kill it. If JK is 1, 0, you want to jump it, okay, and therefore my D input becomes J. Let's say this is Q bar, ORed with K bar Q. And therefore, all you need is a JQ bar, K bar Q, OR them together. That becomes your D input. So I just turned this one into a JK flip-flop. One last thing before we leave the subject of flip-flops alone, meaning that we have covered everything there is to be covered about flip-flops, variation, changing from one to the other type, adding enable, adding reset, adding this and then, and all that. And the one last thing I want to do is talk about the timing. I have a DN and I have a clock. And this happens to be falling edge. What it means is this is my clock, this is my DN. Okay, on the falling edge of the clock, the value of D, whatever it is, will be clocked into Q. And then Q is affected a few nanoseconds after the falling edge of the clock. Notice that my DN is changing at this point, and then I have a falling edge of the clock, the active edge. This is called the active edge of the clock arrives. We say that before the active edge of the clock arrives, you want to make sure that your DN is changed long enough before the active edge of the clock to have a chance to set up itself. And therefore, what I'm saying is, yes, I can change D here, I can change D here, but if I get too close to the active edge of the clock, I am violating the setup time. And therefore, the minimum amount of time between D changing and the active edge of the clock is called setup time. In all your circuitry, in all your timing, you want to follow the setup time. Make sure that you don't change D and immediately clock it. Something bad is going to happen. Something unpredictable is going to happen. Okay? That's one thing. Let's say everything is fine and then you haven't violated the setup time and all that, and the D continues. And D continues and gets into the clock. Okay. And let's say, yeah, let me do this. Falling edge again. Let's say this continues and then becomes 0. So it became 0. And this was changed long before the falling edge, so there was no violation of the setup time. And then it became 1 again long before the falling edge, and so there is no violation of the setup time. Okay? The D remains valid for at least setup time before the edge of the clock. Now the edge of the clock arrives. You cannot be just too much in rush to remove the D. You have to hold the value of D for at least the amount of Guess what? T, hold. Okay? And therefore, the only timing that we have for the flip-flop is setup time and hold time. In all your timings, you want to make sure that this is not violated. And in this case, this becomes 1. Okay? Hit hold time. D, holding after the edge of the clock. Setup time. T, setting up before the edge of the clock. That's one thing I need to say about the timing. Another thing I need to say about the timing, which we have already discussed it, but then see if I have a clock, okay, and I have an asynchronous reset. Asynchronous reset means a reset that acts independently, okay, an asynchronous reset. And I have a DN. Let's say this is reset. This is DN. And this is my clock. Okay. And this is my Q. Reset is active low. Here is active high. Means it becomes 1, it resets. Let's say it's not active. The in is 1. And therefore, this is falling edge. Therefore, Q becomes 1. The in remains 1. The in remains 1. And then the in remains 1, remains 1. Okay? At this time, reset becomes 1. Let's give it a little bit more time. At this time, reset becomes 1. As soon as reset becomes 1, it doesn't require the clock or anything. Q goes down to 0. Even if reset goes back to 0, Q remains 0. Okay, so for the entire time that my reset is active, my Q is 0 and remains 0 unless something else brings it back to 1. And then if this continues on the next edge of the clock, after reset is no longer active, the input of D, which is at 1 value, will go into Q. So that's the timing for this. And then this is because of asynchronous reset. And notice that I don't have a number on the left-hand side of my R. That means this is asynchronous. All right, what we have done is we have covered everything there is to be covered about flip-flops. And then let's use these flip-flops for some good reasons, for some good applications.